Hello students. So we're continuing with rotation. We're into chapter 11 now, but I'm putting together chapter 10 and chapter 11. Furthermore, I'm only going to look at chapter 11, the first two sections. The rest of the chapter you're not actually responsible for, although it's really interesting stuff and really you deserve to learn it. So, okay. So first, a little bit of review. Let's talk about rotational position. If I've got something that's going around, the direction in the x-axis, that's angular position 0. And as I turn counterclockwise, the angular position is increasing. And this would be a quarter revolution, it would be 90 degrees, it would be, I don't know how many radians, somewhere between 1 and 2 radians, and so on. Going the other way is the negative direction. All right, now let's talk about the units and symbols. So when we did linear kinematics, position had the symbol x, and its units were meters. And then now for rotation, the symbol is theta, and the units are radians. Velocity, linear velocity was v in meters per second. Rotational velocity, angular velocity, is omega in radians per second. Linear acceleration is a in meters per second squared. For rotation, it's alpha in radians per second squared. We had inertia, also known as mass, which is, I guess, the letter m, and it's in kilograms. For rotation, we have moment of inertia. The symbol is capital I, and the units are kilogram meters squared. And then finally, we have, in the linear case, we had force, which had units of newtons. But for rotation, we have something called torque, which is in Newton meters, and it gets the symbol tau. That's a lowercase Greek letter tau. Okay. Now, so this is maybe the first time you've seen torque and its units. Notice something strange about torque. The units are newtons times meters, which happens to be the same units as work, right? If I push something linearly with so many newtons over a distance of so many meters, I will have done so many joules of work. But torque is totally different. Even though it has Newton meters, it's not a power, or it's not a work or energy unit at all. Let's look a little more carefully at torques. So a force is a push or a pull. A torque is a twisting force, something that makes something rotate, and it is created by a force relative to a rotation axis. So if I have a wheel and here's the axle or rotation axis, and I apply a force this way, then the torque is going to be r, the radius, out to which we put the force, and times the force itself. So now you can see why you had these funny units, right? R is in units of newtons, R is in units of meters, and force is in newtons, so the units are going to be meter newtons, but we always say Newton meters. All right. Quick example. If the wheel's radius was 0.2 meters and the force that we put there was 6 newtons, then the torque would be 0.2 meters times 6 newtons, which would give us 1.2 Newton meters. Yeah, now we want to start tracking the direction of things. This one's counterclockwise, so that's the positive direction, and the rotation vector, or actually in this case we would call it the torque vector. The torque vector is pointing towards u, so it's a little dot there. That's the vector pointing towards you. Okay. What if the force were downward? Same wheel, but the force is downward. Now the torque is negative 1.2 Newton meters. And that's because the twisting action is clockwise. So the torque vector is pointing, right-hand rule now, it's pointing away from you, and so you get the back of the force, the torque vector. Okay. This is a new concept for you, so let's do some examples. Let's figure out what this torque is. Our our radius is 3 meters. Our force is this way. All right, so how would you do that? Well, the torque, in this case, tau, is going to be the radius, which is 3 meters, times 1.5 newtons. And so it's going to come out to be 4.5, and the units are Newton meters. Right? Oh, and it's positive because it's going counterclockwise. So the torque vector would be the dot pointing towards you. All right. Now, what about this one? You figure it out. It's almost the same as this one, but just a heads up. Is this one clockwise or is it counterclockwise? Is the torque vector pointing away from you or towards you? Use the right-hand rule. Okay, let's move on a little bit. Now, the way I've drawn these up here, notice that these were 90 degrees. This is 90 degrees, but it doesn't necessarily have to be that way. So to take care of that case and just to do a better job of defining torque in general, we're going to introduce a new thing called the vector cross product. So this is not an X, and it's not an ordinary time symbol either. It's called the cross, and this is called a cross product. So when you see this written out like this, it means you have to do this math. You have to take the magnitude of R, right? So the absolute value of R, the magnitude of R. You have to take the magnitude of F and multiply, and then multiply by the sine of the angle between the two vectors. And the order that you think of the vectors matters. In other words, it's the angle from the R vector to the F vector, and you got to be doing it in the right-hand rule, in a way compatible with the right-hand rule. So to try to clarify that, the process is like this. Let's say that you had to figure out R cross F here. One way to think about it is, just in your mind, or maybe with a pencil or something, move the R vector over to here like this. So now it's like that. Okay, we're not moving the rotation axis. That's staying put. But now you can see that you're going to turn the R vector like this, right? If you want to go from the R to the F vectors, you're going counterclockwise, and so that means that you're going to have the torque vector pointing towards you according to the right-hand rule. Okay, so that's what I was trying to say right here. By moving the R vector out, I'm saying here, extend the R vector. So actually, the way maybe the way it might make more sense is extending would be, well, okay, here's the R vector, now I extend it further, and then go like this. But anyhow, the goal is to get the direction right. Let's have an example of doing a cross product. So I'm going to start with an example that based on the first example we did, which is this one here, R was 0.2 meters, right? From here to here was 0.2, and the force was 6 newtons. And the angle, right? If I extend R out this way, then the angle is like so, right? And that's 90 degrees in this case, right? So let's go back down and look at the example. Here it is. Okay, so R is 0.2 meters. The force was 6 newtons. The angle was 90 degrees, and the sine of 90 degrees is 1. So so we know that it's going to be 1.2 Newton meters, and it's going to, the vector will be coming out of the paper. Now, I wrote here in some more detail in the process. 0.2 meters to the right is 0.2 times the I hat vector, which points to the right. And then the force is 6 j hat newtons, and the j hat vector points up. So it's this vector crossed with that vector. And so there's a process here. I'm not getting into it at this point, but there's a process to setting up the cross product that looks like this. All right, so anyway, once you've written that out, we can say, okay, it's 0.2 times 6 times the sine of 90 degrees and get our answer. And then getting back to the I and j vectors, the fact that the force vector is pointing out of the paper, that happens to be the direction of the k hat vector. So that's just yet another way of figuring out the direction. These are the answers to questions 1 and question 2 up at the top. All right. Let's do yet another example. Now the vector, the force, is no longer at 90 degrees to the radius vector. So let's say I have my radius vector extended out like this, right? This is not 90 degrees anymore. Actually, it happens to be 30 degrees. So when you figure out the torque, actually, you know, there's like a little mistake here. This needs to have a vector sign over it. Okay, it's R cross F, which is RF sine theta, which is 10 meters for R, 5 newtons for F, times the sine of 30 degrees. I put that in a calculator, you find, okay, it's 0.5. And so you get the answer, 25 Newton meters, and it's pointing out of the paper. It's counterclockwise, so it's pointing towards you, so it's the dot, and we could also say it's in the k hat direction. All right, so here are some more questions. So let's see, you should think about these for a little bit. All right, what would the angle be for this one? Right, so this is a tricky one. Here's what you want to do. You want to have your R vector continuing out like this, and now the angle, you could think of the angle as being 180 degrees plus 45. You could think of it that way. Actually, I like doing it that way because it's consistent. I'm always going counterclockwise with my R to F angle measurement. If you decide to go the other way, okay, that's fine. You're still going to get the right answer, but just keep in mind that this is a negative angle, right? And so this is going to end up being what, negative 135 degrees. Okay. Now, what about this one here? Now, when you extend this one, right, here's your force, and now you're going to extend your r vector like this. So here's my extended r vector. The angle between them is 0. And what's the sine of 0? It's 0. So you know that the answer to this one is just going to be 0. This one here, it's going to be 4 times 100 times the sine of negative 135, whatever that happens to be. Okay. All right. So, okay, here are my answers on the next page.